Hi, today we're going to go over the 3 solubility classes.
But Chris, what's solubility?
Well, I'm glad you asked, Tibby. Solubility refers to the amount of solute that can be dissolved in a solvent. Does that answer your question, Billy?
Kinda, but can you give me some examples?
Well, examples include soap and water, sugar and tea, and the BP oil spill in our beloved ocean.
But Chris, oil doesn't dissolve in water, it floats on top.
Well, we're measuring the solubility, which is the amount of a solute being dissolved in a solvent, whether it's being dissolved in or not at all. When it comes to biological compounds, there are 3 classes of water solubility. The first one is hydrophilic, and hydrophilic likes water. While the second one is hydrophobic, and hydrophobic is scared of water. And then we have amphipathic, which is both hydrophobic and hydrophilic. And amphipathic compounds are mostly illustrated as a ball and stick, where this is the ball, and we have the stick, and this is the polar head, and this is the nonpolar tail. Hydrophilic compounds are the first one we're going to talk about in depth. And hydrophilic compounds are hydrophilic because their structure resembles H2O, water. And chemical compounds that are hydrophilic have polar groups and are able to hydrogen bond.
But Chris, all those words sound really scary. Can you give me an example?
Well, Billy,
How'd you do that?
with science, Jimmy. Anyway, the topic at hand, hydrophilic compounds include carbohydrates like fructose, which is in this apple, and amino acids like glycine, which is in people like you, Billy.
Wow.
Here we have water and simple table sugar, which is also known as sucrose. And as you can see, when we add them together, the sugar is hydrophilic because it is dissolving within the water.
Is hydrophobic compounds, and hydrophobic compounds are insoluble in water. Hydrophobic compounds are insoluble because, as opposed to hydrophilic, they lack polar groups and cannot form hydrogen bonds, which therefore makes them insoluble in water.
That sounds also complicated. Can you give me an examples?
Why, sure.
Wow, are you a wizard, Chris?
No, Jimmy, a scientist. Anyway, hydrophobic compounds include fats or triglycerides, like the stearic acid or cholesterol.
Water and olive oil. And when we mix these two together, you can see that the oil and the water will become independent of one another. This solidifies that olive oil is indeed hydrophobic or insoluble in water.
And lastly, we're going to go over amphipathic compounds.
But Chris, how'd you change your shirt so fast?
With science, Nicholas. Anyway, amphipathic compounds have both a hydrophobic part, which is called the tail, and a polar head, which is hydrophilic. And as I said before, this can be easily illustrated as the ball and stick mentioned before. When amphipathic compounds are added to water, they form either two different things. One, they have a monolayer where the polar heads align, where the polar heads attract the water, keeping water outside. While a micelle has a ball-like structure that contains the water outside but also emulsifies or contains nonpolar substances like dirt or oil. And this is most found in soaps and shampoos. The most notable example of amphipathic compounds is found in the cell membrane of an animal cell. And the cell membrane is called the phospholipid bilayer, which is two monolayers stacked up against each other, allowing molecules to be transported from the extracellular to the intracellular of the cell, allowing the cell to live nice and happy and healthy.
As a review question, given the chemical formula of gasoline, is gasoline hydrophilic?